Uh, Hello. Welcome everyone to our last probability seminar. After this we'll be having some PhD student and poster present PhD student short talks in the next 2 weeks. So this will be effectively our last probability seminar. We are very happy to have Antti Knowles from University of Geneva, and he'll be speaking to us about spectral phases of Erdös-Rényi graphs. And as usual, it will be two talks, roughly 45 minutes each. And if you have any questions, please feel free to unmute yourself and ask the questions, or post it on chat and I will ask Antti, and we can have some discussion during the break as well. Okay, Antti, over to you.
Okay, well, thank you very much for this invitation and opportunity to give a talk in your seminar. I will talk about recent and ongoing work on spectral phases of Erdös-Rényi graphs. So all of the new results I will present are all joint work with Johannes Alt and Rafael Ducates, who are or were recently postdocs in Geneva. So let me first, my talk consists of, I think, 3 parts. I mean, 4 if we have time, but I think it's unlikely, so 3 parts. The first part, I will give you an overview of the questions I will talk about and of the main results. So the general underlying question is that of this universality conjecture for disordered quantum systems. So let me first talk about the object that I will consider. So that's the protagonist is this H, which is a random Hermitian operator, a random Hermitian matrix. So and from a physics point of view, a Hermitian operator means a Hamiltonian of a quantum system. And so that's the physical motivation, and the randomness models disorder in physics. So you can think of some disordered object like a body, for example, an electron moving around in a metal or a semiconductor. And there's a certain amount of disorder arising maybe from impurities or thermal fluctuations. And so from a mathematical point of view, the study of the quantum mechanics of such systems reduces to the spectral analysis of this Hamiltonian H. And there is a general conjecture. It's a sort of a somewhat vague conjecture, so it's not a mathematical conjecture. You can construct pathological counterexamples, but it's more of a philosophy that under reasonable assumptions, the spectrum of this H should split into 2 different phases. The first one is usually called the localized phase, also the insulator phase, and it's characterized by the eigenvectors being localized in space. I will say a lot more about what that means precisely, but you can think of your physical space as being a box, for example, and then your eigenvector will typically be essentially concentrated in a small region of this box. And the local spectral statistics will be Poissonian. So that means if you now take a portion of the spectrum, you zoom into that portion, you look at the correlations of the eigenvalues, they will be independent, so they don't see each other. And then in the other phase, which is usually called the delocalized phase or the metallic phase, the eigenvectors are fully delocalized, so they're essentially supported throughout physical space. And the local spectral statistics follow random matrix theory. So they follow this universal statistics from random matrix theory, for example, that of the Gaussian orthogonal ensemble. And there's sort of a heuristic for why these things should come hand in hand, why this behavior of the eigenvalues should always be coupled to this behavior of the eigenvectors. And to understand that, let me be a bit more concrete. So let me take lambda, capital lambda, to be a finite set, which I think of as being the physical space, so the space in which your quantum particle can propagate. For example, think of a large box in ZD. And so H is indexed by sites in this set, lambda. And the reason, for example, why these 2 things should be coupled, so why localized eigenvectors are associated with Poissonian eigenvalue statistics, is not so hard to understand intuitively. If you pick 2 neighboring eigenvalues, then with high probability, if the associated eigenvectors are localized, then they will have, with high probability, be localized in different regions of space, and their supports essentially don't overlap. And if the randomness is somehow local in space, which it usually is, I mean, in all reasonable models, then these two different regions of space are governed by independent randomness, and therefore the associated eigenvalues should also have independent distributions. And that gives rise to Poisson statistics. So that's a rather compelling heuristic. In fact, it can be made even more precise. It can be made rigorous in some instances, and it can be used to prove Poisson statistics. And let me now illustrate a bit more what one means by localized and delocalized. So I have plotted here, for the purpose of illustration, I have taken my lambda to be a linear set. So if you wish, a one-dimensional lattice. Of course, in reality, there's typically no such linear structure, but to draw plots, let me assume there is one. And take an eigenvector. So I will call eigenvectors W, and its components I call WX. So X is a site in capital lambda, and I will always normalize my vectors to be to have Euclidean norm 1. And therefore, the map that maps X to WX squared is a probability measure on lambda. It's a random probability measure on lambda. You can try to study its shape. And typically, these are the two scenarios that you expect. So in the localized phase, you expect this probability measure to be essentially localized in a small region. So here it is. Here's a small region that carries most of the mass of this random probability measure. And outside, well, if things are random, let's say the law is absolutely continuous, then with probability 1, every site will carry some positive mass, but this is typically going to be very, very small. And conversely, in the delocalized phase, you expect your mass to be roughly uniformly spread out across the whole system. Okay, so I hope this intuition was sort of clear. So as was pointed out, please feel free to ask questions. So I have, as I said, I don't really have any grand ambitions of actually coming to the end of my talk anyway. So I'm very happy to have questions and to even discuss a bit if anything is unclear.
So this is a sort of a typical eigenvector or eigenvector corresponding to some particular eigenvalue. What eigenvector is this?
Yes, so I haven't yet said which one specifically it is. I am more referring to what these two things mean. So if I say that an eigenvector is localized, I mean, what does it look like? And if I say an eigenvector is delocalized, what do I think of? What should I think of as this thing?
Okay, thanks.
In general, I will of course, you can say maybe all eigenvectors are delocalized or all eigenvectors are localized, or in general, in the most interesting models, some are in one phase and some are in the other phase, and there's perhaps a boundary between the phases.
Okay, thanks.
So we will see a few examples of that. Maybe just before we see perhaps the most famous example, I would like to be a bit more precise. So how can one quantify this notion of localization or delocalization? There are several standard ways of doing that, which are very popular in the literature. I will talk about two, which I think are the most common ones. So for simplicity and throughout this talk, I will call the cardinality of my set lambda, I'll call it capital N. And so the first way of quantifying localization or delocalization is something that and is often referred to as the localization exponent. And in the physics literature, this is also often known as the inverse participation ratio, if you've encountered this term before. So it's a number, it's an exponent, in fact, between 0 and 1, defined as follows. So you take a q, which is bigger than 1, and less than or equal to infinity. And you consider the L2Q norm. So this is the L2Q norm of my vector. I remind you that this has L2 norm 1. And you define it as follows. So you look at how this thing behaves as a function of n. Of course, n is fixed, really. So this exponent, if you wish, is an n-dependent quantity, but it's convenient to take the exponents. In fact, the exponents are typically the things that have a limit as n tends to infinity. And so this is how I define it. For convenience, I include this prefactor. You will see right away why this prefactor is convenient. Now here are three remarks, which are all little exercises. You can do them if you wish. They are all sort of one line or half a line computations. So complete localization, so a vector which is located at just a single site, which is a delta function at a single site, means precisely that this dq is equal to 0 for all q. And if you take a perfectly delocalized vector, which is constant on all of lambda, this corresponds to dq being equal to 1. And you can take, of course, you can take something in between. If you take your w to be uniform, so constant over n to the gamma sites, where gamma is an exponent between 0 and 1, and 0 elsewhere, then this corresponds, in fact, this is implied by dq being equal to gamma for all q. So it's this latter thing that's the reason why we like to include this prefactors. It's chosen precisely in a way that this last remark is correct. So this is a way of quantifying, it's a nice way of quantifying the extent of localization or delocalization, going from 0 corresponding to complete localization to 1 corresponding to complete delocalization. There is another notion which is not equivalent, which doesn't imply or is not implied by the first one, which is often referred to as scarring, which comes from more from the quantum chaos community. And that is, I remain vague here. That is to say, basically, that most of the mass of your eigenvector is supported in a small volume. So you give yourself a small positive number epsilon and a small subset, and you calculate the amount of mass in this small subset, and you say that this is 99% of the total mass. So these are two commonly used notions. I will use both. I will mainly focus on the first one throughout this talk. Let me now give you an example of one of the standard models, one of the perhaps the most studied such models, which is the Anderson model. So some of you are probably already familiar with this model. Let me just recall it. So it lives on a let's say on a finite subset of ZD. So you take the d-dimensional square lattice, and you take a finite subset, let's say a cube in this lattice, and you consider the following operator. So you take the negative lattice Laplacian. This is the usual Laplacian, and you add lambda times a diagonal IID random matrix. Okay, so this V is a random potential, which means it's a diagonal matrix, so that at every site of the lattice you have an IID random variable, and you can take these variables to be just standard normals if you wish. That's fine. And this model is already a very interesting model. So if you know some quantum mechanics, it's sort of reasonably realistic. This is the kinetic part of the Hamiltonian. This is the potential part of the Hamiltonian. So it models really an electron hopping on a disordered lattice, and it exhibits depending on the dimension, a rather complicated conjectured phase diagram. So especially in dimensions 3 and above, you have the following phase diagram, which is so far conjectured. So this is a figure I've stolen from this book, Random Operators by Eisenman and Watson, which is if you're interested in these questions, is a very nice and clearly written introduction to these topics, which I highly recommend. So the conjecture is the following. So so here is the extent of the spectrum. So the spectrum is in this region, in this kind of cone. On the horizontal axis, in fact, all of the plots, such plots in my talk, I will always have the same quantity on the horizontal axis, which is the energy, or mathematically, which is the location where you are in the spectrum. and lambda is the so-called disorder strength, which is the coefficient in front of your random potential. And the conjectured phase diagram is the following, that if lambda is positive, of course, if lambda is 0, then this is trivial. We know what the spectrum of the Laplacian is. Everybody's delocalized. The eigenfunctions are just trigonometric functions on the lattice. But let's take a positive lambda, not too big. Then the conjecture is that the spectrum splits into two phases. So inside this kind of bubble here, you have a delocalized phase. So that's what's meant by this. So there are various ways of expressing this, but in my terminology, this bubble here is in the delocalized phase, and everything outside is in the localized phase. And there is a sharp threshold transition from one phase to the other. And so far the localized phase has been rather well understood in the mathematics literature. There's been a series of great developments over the past 40 years now, starting from this landmark work of Fröhlich and Spencer. And on the other hand, the delocalized phase is open, and it's not just a bit open, it's wide open, in the sense that it seems at present basically hopeless. And I think there's not even the beginning of an idea of how to address it rigorously. However, the heuristics and simulations are very clear that this phase should exist and should be in this bubble-shaped region. So that's the Anderson model. I will now talk about different types of models. There are, of course, many other kinds of models you can define to understand such disordered Hamiltonians. The simplest, perhaps, is the set of Wigner matrices. So you just take a random n by n matrix whose entries are independent, let's say IID, up to the symmetry constraint, which is already a non-trivial model. And there's been a huge amount of activity in the past 10, 15 years on this, and they have by now been extremely well understood and have been proven in great detail to be in the delocalized phase. These models become very interesting if you allow the entries to have heavy tails instead of the usual light tails, let's say sub-Gaussian or something like that. And then, in fact, if the tails are sufficiently light, then it is no longer true that the whole spectrum lies in the delocalized phase, and a localized phase emerges, and this has been studied and is still being studied to the present day. And it's not an easy question at all. Nevertheless, there's been quite a lot of progress in the past 10 to 15 years on this model as well. Random band matrices have also been extensively studied in the random matrix literature. They were proposed as a simple alternative to the Anderson model, since the Anderson model seems somewhat untractable in the delocalized phase. But you take essentially a Wigner matrix and you just set all entries to be 0 outside of a narrow band around the diagonal. And there's been some progress on this. I mean, there's still, the big conjectures are still wide open. For example, to understand something analogous to this picture here in 3 dimensions. But there's been significant progress in both the localized and the delocalized phases for these random band matrices. I give a few references. These are, of course, very incomplete lists, and I will not go through them in detail. If you're familiar with these works, you might recognize them. You have the slides, I think, so you can also have a look at them and look up the references if you wish. In this talk, I will talk about a different family of random operators, which are random graphs, which can be regarded as sparse random matrices. And for that, the prototype is the Erdös-Rényi graph. It's the simplest random graph you can imagine, I think, at least the simplest kind of non-trivial random graph you can imagine. And it's also the prototype of a sparse random matrix through its adjacency matrix. So how is this defined? So this is my notation. So it's the Erdös-Rényi graph with 2 parameters, n and p I write as d over n. So how is it defined? You take n vertices and you consider all possible edges, or all possible edges of the complete graph on these n vertices, and each edge is kept in the graph independently of the others with probability p. Okay, so that's the definition of the model. And as I said, I call this probability p, I call it d over n. I parameterize it using this number d. The d, it's convenient to use a d. The interpretation of d is the expected degree of a vertex. And this is very easy to see. What's the expected degree of a vertex? Well, you pick a vertex and you sum over all edges of the complete graph and times the probability that this edge is actually included in the Erdös-Rényi graph. And the latter thing is p, and there are n such edges for any vertex. So the expected degree is p times n, which is this d. Okay, so again, please ask questions if the model is not clear. I think most of, or maybe all of you already know this model anyway. And you probably know that this model undergoes a a transition, a well-known transition, going back to the original work of Erdös-Rényi, in fact, in the 50s, around the critical regime when d is of order log n. And the original transition uncovered by Erdös-Rényi was the connectivity transition, where if d is much bigger than log, in fact, is bigger than some constant that's bigger than 1 times log n, the graph is almost with high probability connected. And if d is less than some constant less than 1 times log n, then the graph is with high probability disconnected. In fact, it has isolated vertices. And in fact, this is a manifestation of a more general phenomenon that as I will explain, there are other transitions around this scale log n, and all of these stem from the same basic phenomenon, that this is the scale at which the degrees do not concentrate. And that's an easy exercise using some standard concentration inequalities like Bennett, for example. If you take, so you can ask yourself, in which regime of d is it true that with high probability all degrees are close to their expectation, which would be little d. And if d is much bigger than log n, then the answer is this happens with high probability. So with high probability, all degrees are roughly equal to little d. And then in that case, your graph is very homogeneous, it's a very homogeneous, regular looking object. And if d is much less than log n, or in fact less than or even comparable to log n, this is no longer true. And your graph starts looking much more inhomogeneous. You start having isolated vertices, you start having leaves, you start having hubs of very large degree, and so on. So your graph develops structure. And typically, in order to have some localized phase, you need to break homogeneity. You need to have some kind of structure. So one could hope that in this regime, you can have you could have at least the existence of a localized phase. And that's what we would like to understand. So the random operator associated with this graph, well, there are several natural operators you can associate with the graph. Perhaps the simplest one is the adjacency matrix, which is just this matrix. So AXY, it's indexed by vertices, and AXY is 1 if and only if X and Y are connected in the graph, and otherwise it's 0. Okay, so this is my model. Let me now give you an overview of the results that we have obtained for this model. So these are summarized in the form of a phase diagram, which is very similar, or looks somewhat similar to the phase diagram I flashed before for the Anderson model. So it's convenient to rescale my adjacency matrix by 1 over square root of d. So that's going to be my H for the rest of this talk, is in fact going to be this object here. And I will focus on the critical scale. So this density d is going to be equal to some constant b times log n. If you recall, this d of order log n was the critical order of d, and I will have a constant b which multiplies this log n. This constant d is the parameter that appears on my vertical axis, and the parameter on the horizontal axis is the location in the spectrum. So the first statement is that the spectrum is almost, or with high probability, given by this colored region. So the area, the region that's not black. So that's where the spectrum lives. And it splits essentially into 2 rough phases. First one is the delocalized phase, which is the red region here. And that is, the delocalized phase is characterized by this localization exponent. Let me just look at the d infinity. I could do the same thing for any q bigger than 1, but for simplicity, let me just consider this number here. So I'm just taking I'm looking at the L infinity norm, you see, and then I mean I have if you put in q is equal to infinity, this is just n to the minus dq over 2. So that's the object I'm looking at, and all of these remarks remain true. So
one question, Antti.
Yes.
So this exponent characterizing localization or delocalization, it won't depend on the q, is it?
Yes, that's a very good question. It can depend on the q. In fact, if it's a non-integer, and it depends on Q in the limit, then you found something very interesting. You can, it's in fact not very difficult to make a link between this localization exponent as a function of Q and the fractal dimensions of level sets of your eigenvector. So this eigenvector, this is my function here. This is a probability measure on this set lambda. You can consider its level sets at a given height. And you can look at the fractal dimension of this thing, which in this setup just amounts to to saying that its volume is equal to n to some exponent gamma, for example. And you can see through a relatively easy calculation that these fractal dimensions are given by the Legendre-Fenchel transform of this function dq. Okay. And therefore, if you find a dq which has a non-trivial q dependence, you will typically have a fractal dimension which depends. The fractal dimension of the level set depends on the height that you're considering. And in other words, that corresponds to so-called multifractal eigenvectors. And this is something that has been studied, investigated a lot in the physics literature. It's sort of a fascinating phenomenon, which is conjectured to appear exactly at this boundary of these two phases. As far as I know, there are, even by physics standards, there are no analytical arguments for understanding this thing. So the arguments are entirely numerical. People have done beautiful simulations, and it seems quite clear that such a multifractality occurs. But this is beyond any current techniques to understand analytically. And that's what happens if it depends on Q. So the results I will present, you can prove results for all Q, but the dependence on Q is trivial. What I, for example, will prove or explain.
Okay.
So this red region corresponds to a complete delocalization, and the blue region is what we call the semilocalized phase, which is characterized by basically by ruling out delocalization. So this number is bounded by some gamma, which is an explicit function. We obtain an explicit upper bound, which is strictly less than 1. And in fact, it's strictly less than 1 in a discontinuous fashion. So as you approach the phase boundary here, you have this gamma does not tend to 1. In fact, I will show you a plot on the next slide. You will see how this gamma behaves. So this establishes a discontinuous phase transition between the red and the blue regions. And finally, at the very edge, we prove a sort of a subphase of this semi-localized region. We prove a sharper statement that not only is this gamma less than 1, in fact, gamma is equal to 0, and the eigenvectors are essentially supported on a bounded number of sites, even as n tends to infinity. So that's what is usually known as localization. I will explain in more detail. In fact, they are supported in, as in the Anderson localization, they are supported on balls of finite radius, and they are radial functions which decay exponentially. The semi-localized phase emerges only below a certain critical threshold that we call B star, which is this number here, which is approximately 2.59. That's just where it appears. So above that, there is no semi-localized phase, and below that, such semi-localized eigenvectors occur with high probability. Okay, so this is a summary of the results I will be discussing, and they are summarized in this phase diagram. So I ask you to just remember this B star. It was defined here, and the H throughout my talk is this object. Let me now go back to what I was talking about before. So what do our results imply for this localization exponent d infinity? So let me take a section of my phase diagram. So I fix B. I think here I set B to be equal to 1. So I take take my spectrum here. So you see, you will, in the middle of the spectrum, you have a delocalized region, and then you have a transition, you go to the semi-localized region. And so our results say, well, obviously that's, I will, by the way, I'm only zooming in, if you wish, in this area here. I'm only interested in what happens here and around the transition point. Of course, it's symmetric, so the same thing applies here. So in the red region, as I stated, this delocalization exponent is asymptotically 1. Here it is. In the semi-localized region, and the transition happens at 2, it jumps, and this curve here is the value of gamma that we obtain. So you see there's a discontinuity, and it's an upper bound. So we don't know exactly whether this d gamma is equal to this curve. In fact, we believe quite strongly, and we hope to prove at some point that it's in fact below this. It's not on this line, but it has to be below this line, so in this blue region. So this in particular implies the existence of a discontinuous phase transition, and this all the way to the edge of the spectrum, which I call lambda max. Okay, so this is a consequence of our results. Okay, so this was a summary of our results. Let me conclude this overview section with some numerics, which kind of illustrate what's going on, so it doesn't remain, so you know, you have a connection to the actual. It becomes perhaps more vividly clear what's going on in this model. So this is an actual simulation that we did. So the horizontal axis is always the same one. So this is where you are in the spectrum. Now on the vertical axis, we would like to plot something that indicates the localization or delocalization, and so it's done in the following way. So we take a scatter plot. So as I said, the horizontal value is the eigenvalue, and the vertical guy is the L infinity norm of the eigenvector. So the larger this value is, the more localized your eigenvector is going to be. And so the parameters are, well, n, this is basically as big as my laptop will go, and this b is 0.6, which is just a convenient value. So it's somewhere, somewhere here in this spectrum. And you see that there are some interesting things going on. So the red region, if you recall, is the region between 0 and 2, and then symmetrically on the other side. And so here things do indeed appear to be delocalized. The L infinity norm is small. So if things were perfectly delocalized, you would expect this L infinity norm to be equal to, well, its square to be equal to 1 over the dimension. So 1 over 10,000. This is the square root of the square of this number. So you would expect it to be 1 over 100, which is 0.01, which is somewhere down here. So it's higher than that, but this is purely due to finite n effects and random fluctuations. So this height here corresponds basically to complete delocalization. You see that as you, this discontinuity is not really apparent here. We have proved it. So this should really be discontinuous, but the discontinuity has not yet really become visible because n is not big enough. It's actually not easy to do simulations, as you may imagine, because we are on the logarithmic scale, and I think for the purpose of any numerics, log n is a constant, right? Log n is always a constant, no matter how large n is. So it's actually surprising one can even see anything in these simulations, but one can a bit. And as you see, there's something funny happening around 0, and I will talk about that a bit in a while. If b is sufficiently small, we have to exclude also a neighborhood of 0, and that's not just a technical thing. That's really what one has to do, because otherwise the result is wrong. But now as we pass, we go into the semi-localized phase. You see here that the eigenvectors become increasingly localized, and the L infinity norms correspondingly become larger and larger. Okay, so this is a summary of these results. So let me now give you, I skipped one slide, it seems okay. So let me now go to the second part, which is now a slightly more detailed description of these results. So I kind of gave a graphical overview in the context of these phase diagrams. So as I said, this is all joint work with Johannes Alt and Rafael Ducates. To make these statements easier, I will throughout use a sort of a generic parameter kappa, which is a function of n. So all of these results pertain to the limit as n tends to infinity. As the size of your graph, the number of vertices tends to infinity. And this will be some positive number that's little over 1. And we will choose it to go to 0 at a rate that's convenient. So there are some assumptions which I don't want to go into in detail, but this just should go to 0, but not too fast, so that their theorems are correct. So let me first talk about delocalization. So the theorem is very simple to state. The complete delocalization, in other words, this d infinity is equal to 1 in the limit, holds with high probability in the whole red region. So here's my red region. And this red region, in fact, can be described precisely as the union of the 3 following regions. You can, if your d is bigger than b star times log n, the delocalization holds everywhere. If d is bigger than 1 times log n, then delocalization holds provided you stay away from the semi-localized phase. And that's also what we expect. So if I again go back to this phase diagram. So in this region here, so here above this line, all eigenvectors are completely delocalized. Between these two lines, all eigenvectors which stay away from the semi-localized phase here are completely delocalized. We know we have to exclude this phase here because there are some vectors here now which are not fully delocalized. And the final region is if you go below the threshold 1, then you also have to exclude the origin. And that's this statement here. And in fact, you can go very, very far down. You can go further down than any arbitrarily small constant times log n. You can go down to square root of log n. And it's in fact instructive to try to figure out whether this is optimal and whether this condition is required and whether this is optimal and what goes wrong. And in fact, the claim is that this is optimal up to the numerical value of this constant c. And the mechanism responsible for destroying this delocalization, if you go to even lower densities, is the following very nice mechanism that's sort of well known in the literature. I was unable to, I asked several people, I looked in the literature, I couldn't actually find who really came up with this first. Of course, it's not us. I mean, this pre-existed our work by at least a decade. But so unfortunately, I can't really say who came up with this idea. It's a very simple and nice idea, which goes by the name of tuning fork states. So here is the kind of graph that leads to the breakdown of delocalization in this region here. And so you take 2 stars. Here's 1 star of central degree d. So this is the number of spokes that this star has. You take an identical copy of this star, and then you attach them to one common vertex of this giant component of the graph. And it's easy to check that if you take any eigenvector of this star and you take the same eigenvector on the other star with the negative sign, so you just flip the signs of the components, and you set 0 everywhere else on the giant component, this combined function will be an eigenvector of the total of the full adjacency matrix. In other words, this gives you a very explicit construction of a highly localized state. It's localized only in these stars. And it's easy to calculate that such a star, you can calculate the spectrum of such a star. You will find that it has a low rank. It has a positive eigenvalue, which is equal to square root of capital D over little d, where capital D is the degree of the hub of the star. Now you can ask yourself, well, how often do such structures appear with high probability? And it's an easy probabilistic analysis. You can show that if your d is of order log n or below, then you start seeing stars with central degree of order 1. And that's basically why I have to exclude this region here below. And this remains true all the way down to the scale square root of log n. And now and the stars start increasing. So as your graph becomes less and less dense, the stars become bigger and bigger. And eventually, as you reach the scale square root of log n, you start seeing stars with high probability of central degree of order d. And then this eigenvalue is going to be of order 1. In other words, the localized spectrum generated by these stars now starts permeating this entire delocalized phase and destroys the whole delocalized phase. So that's why such a phase diagram cannot hold for scales below square root of log n. Okay, so this was a little remark about optimality of these conditions. Now, conversely, let me now talk about the semi-localized phase. So that was this blue region here, and I'll talk about this blue region. So it can be stated in the following way. In order to state it, I need two things. I would like to introduce a so-called normalized degree. So it's just the degree of the vertex. Alpha x is the degree of the vertex x divided by d. So you can write it like this. The degree of vertex x is just the row sum of the adjacency matrix, and I divide it by d. And I will introduce the following map, which I call capital lambda. So maybe this is not ideal. I use the same letter. It has nothing to do with the other capital lambda I used before, of course. So this is a map which I only used for alpha greater than or equal to 2. So you can check this is a map that maps the interval 2 to infinity into itself, and it's increasing. And the claim is the following. Take an eigenvalue in the semi-localized phase, so bigger than 2, and consider its associated eigenvector. And the claim is that this eigenvector will be essentially supported in a very small portion of the set of vertices. It will be supported in fact, in balls centered around so-called vertices in resonance with lambda. So what does this mean? This lambda is the eigenvalue. You view it as an energy, and we take all vertices such that lambda applied to their normalized degree is close to this energy lambda that I chose. So this is the definition of vertices in resonance. So if you wish, you can associate an energy, capital lambda, of alpha x to every vertex x. And we take all vertices whose energies are close to the chosen energy lambda. Then the claim is that there's a radius, which is large, but not too large. I mean, growing slowly with n, you should think log n or something if you want to be concrete, such that you can define a localization profile vector associated with every resonant vertex x. So I take any resonant vertex x and I define a simple, it will turn out to be a simple vector that I call v of x, which is supported in the ball of radius r around x, such that first of all, these vectors are, in fact, these balls or the vector, let's say the supports of vectors are disjoint. So if I take two different vertices, resonant vertices, the associated vectors have disjoint support. And moreover, W is essentially collinear with these vectors, these profile vectors V of x. So that's a sort of localization statement. So I have these localization profile vectors. You should think of this being a relatively small set. In fact, one can estimate its size. It's not hard, and indeed it's a very, very small set compared to the total number of vertices. So I have a small set of resonant vertices. Each of them carries a single profile, a localization profile, and this eigenvector is essentially collinear, or lies in their linear span. And in fact, one can show that I will give a more precise formula for these v of x's, but these things are radial functions of x, and they decay exponentially around the vertex x. So for example, you have such an estimate. So this is exponential decay. If you take the total mass of this vector outside of a ball of radius r, this thing decays exponentially. Okay, so that's the statement about semi-localization. Here's a picture. So this is how you should imagine this semi-localized phase. This is what it looks like. This is what I believe it really does look like in real life. I mean, in these actual graphs. So this blue is this is of course schematic. It's very hard to draw these graphs. They are not planar and they are very big. So I use sort of intuition coming from, let's say, more Riemannian geometry. I mean, you have a random, in fact, this is all based on the random geometry of the graph. So let me draw this in terms of let's say, more familiar notions of Riemannian objects. So this blue region is my whole graph. I have a small number of resonant vertices somewhere, and I draw these relatively small balls around these resonant vertices. And in these balls, this is where my eigenvector is going to be supported, in these balls. And in fact, it's a rank 1 object. I mean, it lies in a one-dimensional subspace around each one of these balls. Okay, so that's what the semi-localized phase actually looks like. So I hope this gives a rough picture of what is going on there. Let me now talk about, to conclude this discussion on the results, let me talk about this region here. So the edge, the very edge of the spectrum. And here, I mean, you can ask a number of questions. One, there's a classical question in random matrix theory, which is the distribution, the law of the largest eigenvalue of a random operator of a random matrix. This has motivations, strong motivations coming perhaps less from quantum mechanics and more from questions of graph theory and perhaps data science, which I will not go into, but you may know that the extreme eigenvalues of graphs say a lot about the structure of the graph. So these are the sorts of questions that we're interested in. Yes?
Just sorry to interrupt, it's just to let you know it's 45 minutes.
Oh, I see.
Want to take a break now or in a few minutes?
Yes, that's thank you for that. That's probably a good idea. Let's take a break and we can discuss these results after the break. And then after that, I'll give a few ideas of how to prove these things. So yeah, okay. Let's do a break now. Thank you. That's good timing.
Okay, welcome back everybody. So this will be the second lecture by Antti. Antti, you can continue.
Hey, thank you. So in the second part, I will start by talking about a slightly different type of results, which is what happens at the edge of this Erdös-Rényi graph. And then I'll give a few indications about how to prove these results. So at the edge, so now I will be really focusing on this edge, on the spectral edge here, and trying to explain this blue line. So in terms of the localization versus delocalization picture, at this edge, I have localized eigenvectors, which means they are basically essentially concentrated on a bounded number of lattice sites. In fact, the phenomenon, as I discussed at the very beginning, if you recall, the way we approach that, the way we prove localization, in fact, crucially relies first on proving Poisson statistics of the eigenvalues with an intensity that has a bounded density. So these things, as I said, they come hand in hand, and also in our proof, they really come hand in hand. So, and this is perhaps of independent interest, as I said, if you're interested in questions of spectral graph theory, or perhaps data science, where the fluctuations of the top eigenvalues are of some importance. So we have a condition. So we assume that the semi-localized phase exists. So we are below this B star, if you recall. Let me go back to this phase diagram. So we are below this threshold where semi-localized phase will exist. I should maybe point out these gray regions, they have width that tends to 0 as n tends to infinity, but we don't really say anything in them. They have, you should think of them as being lines essentially in my diagram. So, so we are considering the spectrum in this region here below this critical line. So we have some semi-localized phase. You may know this problem has a relatively long history. So the question of the fluctuations of the top eigenvalue of the Erdös-Rényi graph has been studied quite a bit in the random matrix literature, mainly in the past 15 or 20 years even. And it's an interesting question. So if you're perhaps I should mention this orally. If this parameter d, so if this parameter d is sufficiently large, and let's say if it's of order n, then this adjacency matrix basically looks like a Wigner matrix. And in that case, you would expect, and you can prove, that you get the same law for the fluctuations of the top eigenvalue as for Wigner matrix, which is the Tracy-Widom universal distribution. Now, as you start making your graph sparser and sparser, something interesting happens when d passes n to the 1/3. So when d is between n and n to the 1/3, nothing changes. It looks exactly like a Wigner matrix. As d passes n to the 1/3, the Tracy-Widom fluctuations are in fact replaced by normal fluctuations, by Gaussian fluctuations. So you have a transition where the top eigenvalue suddenly has normal fluctuations. And this is known down to n to the, when d is of order n to the epsilon. I would bet that this remains true for d bigger than log n, although this could be very difficult to prove. So this has been not proved yet. This has not been proved yet. And what we analyze is what happens below that threshold, and we prove there's yet another transition. And below this threshold, when d passes b star times log n, you get a new family of fluctuations. In fact, it becomes Poissonian. And that's what I'm going to describe now. So the statement is relatively simple. It just converges to a Poisson point process. The lower bound here, you should not take it too literally. We can go down to relatively sparse graphs. In fact, I think we can go down to graphs which are even sparser than that. This was not our goal here, and this we probably will do at some point. So there exists deterministic numbers which are a bit complicated to state, so I don't want to state them, but they have all very explicit definitions. So they are explicit functions of d and n. There are these quantities that I call u, sigma, tau, and theta. They basically tell you how to rescale your process. So here is my eigenvalue process. So I consider all the eigenvalues of my matrix H, and I have to recenter and scale them. So I take this, I recenter it by sigma. So sigma, you should think of it as being essentially the spectral edge here. So sigma is the spectral edge. Yeah, so that's the thing around which you have to center your spectrum. And tau is the scaling factor by which you should blow up your spectrum. So you sort of, you zoom in and then you blow up. And you notice you should blow up by tau is going to be of order 1, so you should blow up by something proportional to d. And you put a delta mass at the location of every such rescaled eigenvalue, so you get a point process. And this is simply the eigenvalue process of your matrix. And the claim is that this eigenvalue process converges in the sense of a convergence of point processes in some nice metric, which metrizes this topology, to a very explicit Poisson point process, in fact, which I call psi on R, and the convergence takes place on basically on intervals. So it pertains to the edge. So it takes place on any half infinite interval, which contains typically at most capital K points. And this capital K can think of it as a constant. In fact, it can go up to square root of log n. So you can analyze the joint convergence of up to square root log n eigenvalues. And so from that, you get asymptotic equality law, the convergence of the largest eigenvalue, and so on. So basically this tells you that the point process of the top eigenvalues is the same as that of a Poisson, an explicit Poisson process psi. So in order to understand how these eigenvalues behave, I should tell you what this Poisson process psi is. And the psi is determined or any Poisson process is entirely determined by its intensity. So this is the intensity of my process psi. In fact, it's a very simple function. It's a very simple form. So it is basically a superposition of Gaussians. So my G of S is the normal density of a standard normal Gaussian. Right? This is the density of the Gaussian distribution. And what you do, so this is the intensity at location S. So you take your Gaussian at S and you shift it according to this lattice. So the size of the lattice is this parameter theta. If you recall, I had this myriad of parameters. Theta is one of them. So theta is the scaling factor of my lattice. And then I will sum over all integers L. And so I shift, I take this Gaussian and I shift it on this lattice. And I also have a shift by this number du, which lies between -1/2 and half. U was again some explicit quantity that's not so important. Basically, think of it as the largest degree of your graph. And this is just the periodic representative of this number, which can be very large in this interval -1/2 to +1/2. And don't just sum these Gaussians, I weight them. In fact, they are geometrically weighted. And as follows. So I take U, so the Gaussian with integer index L is going to be weighted essentially proportional to U to the L. So if L is U is bigger than 1. So if L is very large, this thing will have a huge weight. And this is as you go towards the negative real axis. So, so this is of course an infinite measure. It's locally finite. It's easy to check. This is a locally finite measure. And its mass from any point to plus infinity is always finite. But as you go towards negative infinity, the mass of this thing tends to infinity, or the density of this thing tends to infinity. Okay, I mean, you can also read it. Is it clear? Does it make sense what this thing looks like? I've plotted here, so I'll give you a few plots. So one thing that's maybe of interest for the following discussion is that all of these parameters, if you recall, we had 4 parameters, U, tau, sigma, and theta. They all scale as follows according to this parameter, log n over d. So if we had the critical scale where this t is constant, this t would be 1 over b. Think of this as being a constant, then these things are all of order 1. And if you go into very sparse graphs, so far below the scale log n, t tends to infinity, and then these things start diverging. So let's try to understand this point process and look at what does the intensity look like in different regimes. So if we now focus on the critical regime, where d is of order log n, that means t is of order 1, and all of these things are of order 1. Then you can just plot this thing. It's just a superposition of Gaussians which are geometrically weighted as you go towards minus infinity. And this is the intensity or measure of this Poisson process psi. And this is, so it looks, so for example, the distribution of the largest eigenvalue is given by the distribution of the largest point of this Poisson point process, which has this intensity. And it's a funny thing. So usually, the mantra is when you have extreme value theory, then you get, you have this general theorem you probably know it, unfortunately. I think it's the Fisher-Gnengo-Tippett theorem, right? So it says that the limiting distribution of the top, the largest point, has to be one of 3 different universal distributions. And in particular, in this case, the conclusion is not true. So it's none of these 3. It's a funny new function. As far as I know, this function has not appeared before in the literature. So you get a Poisson process with a sort of new intensity, which, as far as we know, had not appeared in any other context before. It's just given by this. Now you can try to go to sparser graphs. And then things look perhaps a bit more familiar. So what happens if this t now starts tending to infinity? Well, you can play a game. I mean, this is in fact an exercise. I will let you do it. It's perhaps more instructive than listen to me explaining to you. You can just take this thing and see what happens as t tends to infinity. You see, this u also blows up. So that means that with these Gaussian things, you will have one, in the generic case, you will have one of these Gaussian weights, which has a Gaussian bumps, which has a huge weight, and the one to its right has a negligible weight. Or if you are very unlucky or lucky, and if you find yourself at a particular resonance where this thing is precisely equal to 0 for some L, you will have one Gaussian bump which has weight of order 1. The next one has vanishing weight, and the one to its left has diverging weight as t tends to infinity. And so these are the cases. So if you are in this particular case of resonance, then this is what this intensity looks like. So you will now, in fact, this is the tail distribution function. So the integrated version of this psi. So the mass to the right of my point here. So here's your first bump, first non-vanishing bump. And here comes the second bump, which is enormous. And in this case, it's easy to see you don't get a Gumbel law. This would give you a Gumbel law for the top eigenvalue, but this kind of gives you an extra point, which is far away, which occurs with probability 1/e, for example. So it's a slightly funny distribution. But if you are off resonance, then you just get here and you go from 0 to a huge Gaussian bump. And this is standard extreme value theory, and this gives you a Gumbel law. So the conclusion is if d is much smaller than log n, and you do not have this particular resonant condition for your degrees d. In fact, u is an explicit function of d. So this is purely a function of d, of the edge probability of your graph. So it's a funny thing. If you choose your edge probability to lie on a particular resonant lattice, then you get these kind of phenomena. And if it's off the lattice, then you get a Gumbel distribution.
Two clarifications, Antti.
Yes.
One is if you take your d very close to b star log n, then does it mean that the centering is actually 2 itself?
So if you take your d to be very close to b star log n, yes. So can you repeat the second part? So does it mean that
then the centering sigma is like really like 2 itself?
It's very close to 2. Yes. So we cannot reach 2. In fact, it's not correct if you actually got to 2, but we can get 2 plus little of 1. So really, we can tend towards 2.
Oh, okay. And then if you don't do any centering or different, you would probably get in the bulk or in the pink region. You will, if you try to capture the eigenvalues, then it's like a GUE or what you said.
Yes, that is a very good point. So what you said is I believe to be true. So if you go here in this pink region, that's what you would expect. We've done simulations. We see GOE. That's what you would expect. It's I mean we are thinking about proving this as well. We've thought about it a bit. It's not as easy as one might think and as I originally thought either.
Okay.
I'm pretty sure it's true, but I'm not sure we can prove it. We are sort of trying a bit, but it's not. It's not obvious. So you know that as you probably know, there are some very powerful and general techniques developed in the random matrix community to prove universality in the past 10 to 15 years, which is the kind of a very general way of proving these kinds of statements. But there are some significant issues in applying any of these ideas to these models, which all stem from the sparsity of the matrix. And you might think they're just technical issues, but actually they are not. So there's some real sort of fundamental problems in applying these standard universality techniques. But I agree with you, that's what you would expect, and I'm sure that's what you get.
Okay, thanks a lot.
Okay.
One question, if I may ask. So this intensity is, I mean, it's like it's a compound Poisson or something like that, right? They have a superposition of several intensities. Individually, some of them give Gumbel. Is that what you're trying? Is that what you are saying? But
it's. So when you say compound Poisson, do you mean something like a Cox process with a random intensity? Or?
No, I mean, no, it's a union of Poisson processes with your intensity is a sum of several things, right?
Yes, okay, you can view it like that, yes. Mm-hmm.
And is it that the individual components would give Gumbel, but is that the correct way to think? In the next slide, you had something about something being Gumbel, but something else.
I think you can view it like that. Yes, I think that's a good observation. I think you can view it like that. Yes, so you would have a superposition of many different Poisson, infinitely many different Poisson processes, each of which has a different intensity, and each of these processes individually has a Gumbel top distribution. Yes.
Okay.
Right.
This is, I mean, you may have explained, but I really do not understand this angle bracket du. Exactly what
Oh, maybe I didn't explain very clearly. It's a very trivial object. So you take any real number, and then you you just subtract or add integers until you hit this interval here.
Okay.
So for example, if you take 3.4, then this angular bracket of 3.4 is 0.4.
What does it mean when you put it on du?
Well, du is a real number.
Oh, sorry. So oh, you just take the fractional part. Okay.
Yeah, I mean, you see, it's kind of for convenience, because this L I sum over all integers.
Okay.
So in fact, in this sum, I could even drop it if you wanted. I could even drop it. I think it's a bit more transparent, because when you try to analyze which bump has the leading contribution, then it's natural to say the bumps around L is equal to 0.
Okay.
Otherwise, this number is huge. But you see, just by translation invariance in this sum, you could just rename the variable here and forget about this.
I see.
Angular bracket, yeah.
Sure. Thanks.
Okay, and once you have proved this, you can deduce, in fact, by relatively standard techniques, because you have a Poisson process for the eigenvalues with bounded density, you can deduce the following thing. You can deduce that the probability of two eigenvalues being close to each other is very small. You get this sort of Wigner type estimates. It's one way to prove Wigner type estimates, is to establish Poisson. It's perhaps an overkill in typical applications, but in this case, it's the only way we found. And once you have done that, you can prove that any eigenvector associated with these top or bottom eigenvalues that the previous theorem applied to will be fully localized. So in other words, there exists a unique, so for you pick any eigenvector of your matrix, which corresponds to the top eigenvalues, then with high probability, there exists a unique vertex X such that it's localized around this vertex X, and more precisely such that the eigenvector is close to this localization profile vector V that we talked about before. So it's localization around a single site. And here I make a remark. So if you recall, these were these vectors that we already talked about here. I was not very explicit. These were these exponentially decaying profile vectors. One can be, in fact, a bit more specific in this case, that this vector really is of the following form. So this is the sphere of radius I around the vertex X in my graph. I take the indicator function on this sphere and I normalize this thing to be a unit vector. Okay, so I take a sum over all of these radii. So I take a sum over shells of increasing radii, and each shell is weighted by this function ui, which is a very simple exponentially decaying function in I. Okay, so it's defined as follows, and then I have a recursion like this. And since alpha x is bigger than 2, this sequence is exponentially decaying. Okay. So this was what we have understood at the edge. So let me now go to the third part of my talk and explain a few ideas of the proof, in particular of how to understand this localized phase. So the basic intuition, which I think you already got from the statements, is that there's a one-to-one correspondence between, at least in the semi-localized phase, between eigenvalues on the one hand and vertices of large degree on the other hand. And so in order to make the proof work, there are two basic steps you have to do. The first one is you have to understand the fluctuations of these eigenvalues associated with the large degree vertices. And then you have to establish a one-to-one relationship between these eigenvalues that you've understood and the eigenvalues of H near the edge. So this is perhaps somewhat vague. I will give a few more indications about how to do this. So let me talk about step one. So what does this entail? Let's take a vertex in this set U. I will use it a lot, so let me give it a name. It's just all vertices in the whose normalized degree is greater than 2. And a very convenient way to analyze these things locally is to do a so-called tridiagonalization of your matrix. So what we would like to do is to do an analysis of the graph in some neighborhood of this vertex X. So a nice way of doing, it's not mandatory, but it's actually quite convenient for many arguments, is to try diagonalize this H, if you recall, was just a renormalized adjacency matrix. And what does tridiagonalization mean? I mean, it's a well-known tool in numerical analysis and random matrix theory. It's a very nice tool, especially when you're looking at the largest eigenvalues. And it's a very simple thing. So it just means that you will write your matrix H in a new basis, which I call little h0, h1, h2, and so on, which is an orthonormal basis, which you obtain simply by taking the standard basis vector at the vertex X, so a delta function at X, and then you apply H to this, and then you apply H squared and H to the 3. So you iterate, you take the iterated powers of H, and these form a set of vectors. Now, unless you are very unlucky, these things will be linearly independent, at least the first, let's say, R of them. So this will be a cyclic vector for H. And then you can just do Gram-Schmidt. You can apply Gram-Schmidt to this sequence of vectors, and you will get what we call H0, H1, H2, and so on. And you can check if you haven't done this before. It's an exercise which I recommend. It's a very instructive thing. To check that the matrix you obtain, so if you write H in this basis, the matrix you obtain is tridiagonal. So in other words, the non-zero entries can only appear on the diagonal and on a line just above the diagonal and just below the diagonal. If you're at a distance more than 2 from the diagonal, the entry must vanish. And tridiagonal matrices are extremely amenable to various techniques, most famously orthogonal polynomial techniques or transfer matrix techniques. So you can apply transfer matrix techniques, which is just an analyzing products of 2x2 matrices, so things become much more tractable. The problem here, if you try to do that, is that you can try to find what this basis is, and you will find that it's actually very complicated for this model. And it's very difficult to control the resulting tridiagonal matrix with any degree of precision, certainly with the degree of precision required to prove any of the theorems that I stated. So in principle, it's a nice approach, but in practice, it just becomes too complicated. Maybe if one were very, very strong technically, one could push it through, but it really becomes a nightmare. So we had to find something a bit different, and the inspiration it's from the following toy model, which is another very simple observation, is that consider what we call a rooted regular tree. So what is that? It's a tree. Okay, here's my tree. And it has a root. It has a distinguished root, which is this red vertex. And by regular, we mean that the degree of any vertex can only depend on its distance to the root. So in other words, all vertices in the same sphere must have the same degree. So for example, the root has degree 4, then these green vertices have degree 3, and all the blue vertices have degree, sorry, I'm counting the number of children. So this has, okay, so this is degree 4, this is degree 4, and this is degree 3. Okay. And so here is an exercise which shows one of the things why such trees are very easy to analyze. And that is that if your graph, so this is my Erdös-Rényi graph, if this graph restricted to the ball of radius r around my vertex x, if it were such a rooted regular tree, then this basis would be extremely simple. It would just be the indicator function of the sphere of radius. This is a simple exercise. It's not hard to show it. So this is always true when I is equal to 1. And now basically when I is equal to, well, I recommend you to do the exercise. It's like 2 lines, and it kind of shows you why this kind of tree is distinguished. In fact, it's basically an if and only if condition. So it distinguishes this kind of tree as the graph that has this very simple property. So now here's a natural idea. These in the original graph, these things are too complicated, but let's hope, since these Erdös-Rényi graphs are known to be locally tree-like, let's somehow hope that they resemble sufficiently closely such a rooted regular tree. And let's kind of, instead of writing this matrix in this true tridiagonal basis, let's write it in this basis here and see what happens. Of course, it's no longer going to be tridiagonal. So let's write it in this basis here. We get an almost tridiagonal matrix. So of course, now it will have some elements of the tridiagonal, which are non-zero, which you can estimate. However, here the problem is that these elements will be too large. So the non-tridiagonal part of this new matrix is too large for the argument to work. And so this doesn't work either, unfortunately. But you can improve this a bit to get something that actually does work. And the observation is the following. Let's assume this neighborhood is a tree, not necessarily such a regular rooted tree, but it's just a tree. And this, we know with high probabilities, is true if your radius is not too large. So that's a reasonable assumption. And now you look at this vector. So this is the ith vector in this sequence here that we use to tridiagonalize the matrix. And we just observe that this is kind of a trivial observation based on expanding this thing. You can decompose it as a sum over simple walks on the integers of length I. And whereby a jump to the, let's say, to the right of the walk corresponds to increasing the distance from the root. So how do you do that? I mean, you just, I think it's easiest to explain here. If you are, for example, on this sphere here, and you apply an H on an adjacency matrix, then you can either go out to this neighbor here or that neighbor, or you can go back in. And then you will split all terms, the terms where you go out, or the terms where you go back in. And if you go back in, then you will index that by a walk that takes a step to the left. And if you go outwards, then you will index it by a walk that takes a step to the right. And now we can go back to our previous two attempts. The basis, the original basis here, this true tridiagonalization basis, takes into account all walks. And this simple basis, which is just the indicator function on the sphere of radius I, keeps only those walks that always step to the right. And the thing that works is to take an intermediate basis in terms of these walks, where you define a new basis that we call Fi, where you can take at most one step to the left. So you in this tree picture, when you look at h to the 20, for example, then 19 times you always have to go outwards, but you're allowed to go back inwards once, but only once. And then you have to continue going outwards. Or if you wish, you can just go outwards all the time. And you can calculate explicitly what these vectors look like. So here is an example, for example. So the first two ones are the same as this. The third one is a bit different. So in addition, you will get a contribution. So you have something on the sphere of radius 3, but you also have something on the sphere of radius 1. And more generally, if you consider Fn, then you will have this the indicator function on the sphere of radius n plus an average of something over the geodesic going back to the root from where you are. That's what these things look like. And it turns out that these things do the job, and so that's what one can prove. And to get the following proposition. So choose this R, which is, as before, is a radius which tends to infinity, let's say slowly, and define M to be my matrix I'm interested in this basis that I just constructed. Then I can show that in operator norm, this matrix M is close to the following tridiagonal matrix. So we know that this M is not exactly tridiagonal because I discarded some walks, and therefore I did not take the true tridiagonal basis. However, the off tridiagonal part which is captured by, in part captured by this thing here, is small, is sufficiently small. And in fact, recall that the scale of the fluctuations that we are trying to analyze are of order 1 over d. So if we can go below this scale, so this c is going to be some positive constant, some small positive constant. And so we compare this to this tridiagonal matrix that I call Z. The Z depends, it's a explicit tridiagonal matrix that depends on 2 parameters, alpha and beta. And the arguments I have to put in are the alpha that we already know, which is the normalized degree. So you can write it as the size of the sphere of radius 1 divided by the d. And beta is going to be the same thing for the sphere of radius 2. So it's the sphere of radius 2 divided by the sphere of radius, size of the sphere of radius 1 times d. And these are quantities whose expectations are all 1. And you can put them in this tridiagonal matrix. So this is the definition of my tridiagonal matrix, Z of alpha and beta. So you have zeros on the diagonal, zeros off the tridiagonal. These are all zeros. And then you have square root of alpha, square root of beta, and then you just have something which is almost equal to 1. In fact, it's the square root of this quantity here. And you see, unfortunately, we can't afford to replace this by 1 because the error we would get would be of order 1 over d, and we are aiming for something better than that. And here's a remark: you can do this as an exercise if you wish. Is that this matrix, this tridiagonal matrix, if you multiply it by square root of d, this is exactly the tridiagonalization at the root of the rooted regular tree, so of a tree of this kind, which is an exact tridiagonalization of a tree of this kind, where the root has degree alpha d. So the green vertex has degree alpha d. Sorry, the red vertex has degree alpha d. The green vertices all have degree beta d. And surprisingly enough, the blue vertices, in fact, let me say the number of children, the blue vertices have d+1 children. You would expect that the approximation that works is the one where all the children, if you go sufficiently far into your tree, you start exploring typical vertices. I mean, eventually with high probability, you will start, these guys, they connect randomly to vertices in the graph, and you would expect them to connect to typical vertices, which would have an order d children. In fact, they have an order d+1 children. This is just how the proof works out, but this has to be like that. If you replace this d with this d+1 with a d, you would get something that's wrong here. And this change from d to d+1 is somehow an expression of the fact that we are approximating a tree, which is this neighborhood here, the neighborhood of my true Erdös-Rényi graph with such a regular tree. And this is just not regular. And when you approximate a non-regular tree with a regular tree, you make a systematic error, which induces a bias. Somehow the irregularities don't cancel each other out. It introduces a bias, and that's why we have to change somewhat the degree distribution of the children. But that's the interpretation. But this is the main estimate for this result. And now, well, you have another exercise, which is to figure out the eigenvalues of this tridiagonal matrix. That's not particularly hard. I mean, you basically have to solve a quartic equation, but it's of a nice form, so you can do it, and you can basically say anything you want about the spectrum of this guy here. So you can put, you can do this, and you will find, for example, that this matrix, this tridiagonal matrix, has a unique eigenvalue bigger than 2 plus kappa, and the associated eigenvector decays exponentially. Now, what you will try to do is you go back to the original graph. You say that I invert my basis transformation. Yeah. So I understood the spectrum of this matrix here, and I've understood its eigenvectors. And this matrix was the matrix I was interested in the new basis. So let me go back to this original basis of Fi's. Here it is. This is what I do. and I define a vector y. And this vector y is now the candidate for an approximate eigenvector of my matrix H. And then you can check, indeed, it is an approximate eigenvector with a sufficiently small error, and here is my approximate eigenvalue. So in other words, this is an explicit elementary function of these alpha x's and beta x's, and you have shown that these explicit guys are approximate eigenvalues of H. And then the step 1, if you wish, is concluded by analyzing the fluctuations of these guys. So that was the step 1, which in some sense was one of the steps. The step 2 is somewhat tricky. If you recall, let me go back to these steps. So we wanted to characterize the fluctuations of an eigenvalue associated with the vertex of large degree. So this was purely a local problem. We just looked at the neighborhood of some vertex. We didn't have to consider the global structure of the graph at all. In order to prove any of these results we talked about, you have to take into account the global structure of the graph, all the other vertices of higher degree, how they're connected to each other, and so on. And this requires some more work. I mean, you have to ensure a variety of things. You have to ensure, for example, that these candidate eigenvectors are orthogonal. There is a technical thing which sort of sounds a bit silly, as if it shouldn't be a real problem. I didn't really talk about the probability estimates. I just talk about with high probability, so probability tending to 1. But as you may imagine, in all of these arguments, you have to do lots of union bounds. And if you want to do union bounds, you have to make sure that your probabilities are sufficiently small to survive them. And in fact, both of these things are wrong. So these things are not orthogonal. These balls will typically overlap. And the bounds with which one can establish such results here. So the question is, what is the probability with which this holds? This, I think it's basically sharp, is just not very strong. And if you now try to take a union bound, and these events are basically independent, so you can't beat the union bound, you will fail. So I think you cannot say that such bounds hold simultaneously for all vertices X. So you have to do something to overcome these issues. To overcome the first issue, let me start with the second issue. And with the first one. Let me start with the first one. That these balls in general are not disjoint, and they will typically look like this. So if you take your set U to be sufficiently large, in particular, if you want to cover the whole semi-localized phase, then these balls typically will not be disjoint. In fact, they could even be connected. The centers could even be connected with an edge, or they could have a short geodesic. So we have to do a pruning. I mean, it's a relatively straightforward thing, right? You just cut all the edges that you don't like, that connect two balls of large central degree. But you have to be very careful when you prune, right? Because if you remove even a single edge from your graph, you can check generically, just by, this is perturbation theory, and this is the truth in general, you will perturb the spectrum by an order 1 over square root of d. And remember, the precision we are aiming for is 1 over d, is even better than 1 over d. So this is in general a very delicate thing which you cannot do. So you have to make sure that you prune these graphs, but you have to also be very careful to prune in the right places. So prune in a conservative way and in the right places, so that the actual eigenvalues you're interested in are not perturbed by more than 1 over d to the 1 plus c. So much less than this naive. Let me perhaps skip this, since I think I should probably stop very soon. So let me conclude by giving you a sort of an overview of the structure of how one concludes the whole thing. So this can be nicely summarized. All of the estimates needed for the proof can be summarized in the following way. So how do you solve this issue of union bounds? You have to do in fact, I should talk a bit about this. You have to do a rigidity argument on different scales. The problem here let's see, these bounds here. I told you that these cannot be hold with sufficiently high probability, sufficiently high that I could do a union bound over all x's, and that's just the truth. So the idea is relatively natural. You derive such sharp bounds only for the very largest ones, a small number of them, so that you can still do a union bound. And then you go to a slightly different scale. You go below this, you go slightly into the spectrum, and then you content yourself with slightly rougher bounds. And then you go on. And essentially, I mean, it's sort of a multi-scale argument in the spectrum. In essence, you can reduce it to 3, if you want to, roughly, you can reduce it to 3 different scales, whereby as you go into the bulk, your error bounds become weaker. This number becomes weaker, but the probability with which these estimates hold becomes stronger, so that you can do union bounds. And that schematically can be represented as follows. So you partition all of these vertices you're interested in into 3 sets, U0, U1, U2, where U0 is the small set where you have very fine estimates, and U2 is the largest set where you have very rough estimates. And there's sort of a schematic picture where these are, so these are the quantities we are comparing to. So these are the values of this lambda delta applied to the corresponding function of that vertex. So here they are. Now the blue is the small set where we have very precise bounds. So these cones indicate kind of the accuracy of the error bounds. So we know that the actual eigenvalue has to lie within this cone. And then we go to the green one where the cones are much wider, and the red one, that's the coarsest set, which is the biggest one. We don't know much. It's a very rough error bound. And you just have to make sure that these green and red error bounds are sufficiently strong to preclude the possibility that these eigenvalues would come and mess up the edge of the spectrum. So that the edge of the spectrum is genuinely characterized by the blue ones, of which there are few and for which you have very precise bounds. So that's roughly sort of 1/2 of the proof. The other half, which I will not talk about, is you also have to ensure that these black eigenvalues that I drew in black stay where they should be. In other words, they don't come here. And that, perhaps if I conclude on this, you can do this block diagonal representation where you put, if you do an appropriate change in basis, you will have a diagonal matrix here where these are all the approximate eigenvectors associated with the very precise. So this very precise scale here, the blue ones, and then you have the medium scale and the coarse scale. But you still have a large block here, which is sort of the sea of the sort of the background of your whole graph, which basically is the background. You can view it as the projection of your graph onto the orthogonal complement of all these localization profiles. And you have to prove that this thing is small. So this thing is small in operator norm. And there is a sort of another argument which one has to do for that, which is a lengthier business, which I will not go into. But once you have done that as well, you can put everything that I talked about together and conclude relatively easily basically all of the statements I made about the localized phase. Okay, I think my time is up now, so I will stop. I think this is a good point to stop, so I'll stop here, and thank you very much for being here and for inviting me.